Good morning and welcome, everybody. Thank you so much for joining us for today's webinar, Adaptation of AI and our IR Imaging and Energy Audits and Target Retrofits. My name is Claire. I'm the Deputy Registrar at the OAA. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. Before we begin the webinar, I'd just like to share some important housekeeping matters. Note that we are recording the session for quality and educational purposes. To maintain a stable internet connection, we've muted your microphones and disabled your video feeds. However, we do encourage you to participate through the Q&A window. So you'll see there's a Q&A button at the bottom of your screen. At any point during the presentation, please feel free to submit your questions for the speaker, and those will be addressed at the Q&A period. If you would like to receive Crown Learning Hours, you must attend at least 80% of today's webinar. And if you do so, you will be accredited those hours. Just allow for a week or two of processing time. We have closed captioning services that are available in multiple languages. And lastly, please note that our presenter today does not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. So now I am excited to introduce our speaker for today. Please welcome Raisa Nekhaeva.
Thank you very much, Claire. Thank you so much, everyone, for coming. It's my pleasure to be here. And I would like to start this webinar with a small poll of questions that will come up on your screens. If you could please answer those questions, and then I would like to see the results, just to gauge how familiar the crowd is with the topic. Thank you. And once everyone is voted, now we can see the response that this topic is going to be very new and exciting for you. So I'm very glad to be here and share some of my knowledge with you. We will be discussing today energy modeling, thermography, AI and data processing, among other things. But first, I would like to open this presentation with just a little information about myself. So my name is Raisa Nekhaeva, as Claire has introduced me, and I'm a head of building science at a company called QEA Tech. I have experience both in architecture and civil engineering. I received my architectural studies bachelor from Daniel School at University of Toronto, and then also I'm currently receiving my Master's of Applied Science in Civil Engineering. And my research particularly was around energy models for the buildings and calibration of these energy models via data-driven techniques. So just to situate our conversation, I would like to talk to you first about energy sector and how much buildings participate in the energy sector. And I'm pretty sure that you've seen some of those numbers before. But we can say that buildings are responsible up to 50% of global energy use. Some sources would claim as low as 30, some sources will claim as high as 70. So there is a range of numbers depending on which statistics we're looking from and which country. but I would say it's safe to say that about 40 to 50% of global energy use is due to buildings, their construction, and their maintenance and operation. And out of those energies that we're using, 40% of the GHG emissions can be accredited to buildings, and again, their construction, their maintenance, and their occupational uses. So this are very significant numbers. And when we start thinking about our energy and how we use our energy in the buildings, we need to address particularly our existing buildings, because we have our built environment that we really love and that we want to keep. But to be able to minimize the energy consumption of those places, we need to see what we can do about that. So there are a couple of directions that can be taken. First of all, there are a number of philosophies that are emerging in regards to the built environment, where we can try to introduce passive design strategies to the existing systems, where we can modify consumptional habits, and then when we can address mechanical efficiency, upgrading our mechanical uses. And then we can also rely on some of the certifications that we have and that existing and that are becoming popularized amongst the industry, such as LEED, BREEAM, and Passive House accreditations. And then we're also trying to push for our regulations to be more proactive in minimizing energy consumption in the buildings and making our buildings more energy efficient. That's done internationally with the different codes, and locally with different suggestions and requirements. Like we have our national building codes, national energy codes, and then we also have ASHRAE guidelines and other resources. So this is just simulating what we'll be looking at today at a higher level. And to organize this into different subtopics for our learning objectives, today I'll introduce you to some of the new technologies that are available on the market that are becoming more reliable as they are passing through their tests and verifications and becoming more utilized across different professionals. Then also, why do we have the need for targeted retrofit, and how particularly those energy audits can help us with making the best of our bucks when we're working to optimize energy efficiency in the buildings. Then application of the building envelope energy audits and adaptation of sustainable building strategy. So what can we do in the targeted retrofits? Just to walk you through the presentation structure, we'll talk with you about the principles. So how these technologies meet with energy consumption in the building and how energy audits can be useful to us. We'll look at some of the ways to collect the data in the new ways that would be more time efficient and will allow us for better accuracy in our analysis. Then the actual analysis and interpretation, how does AI and artificial intelligence in general can help us make our analysis more precise, more efficient, and help us make more educated decisions about our existing buildings down the line. So we'll look through the application of those different energy audits and how different professionals in the industry are using them. Then I'll introduce you some of the case studies, and those case studies have been chosen because of their either landmark characteristics or because of some particularly interesting caveats in the process itself. And then we'll close off with conclusions and questions. So part number one, principles. If we think back about the diagram that I showed you a little earlier, making existing buildings more efficient, what would be the way for us to do that? And one of the things that I want you to think about before we go and do the decisions on how we're going to change them, first, I believe we need to do a careful assessment of the conditions that building is currently is, because when we're thinking about our built environment, especially older buildings, you might know it's very hard to come by of the original drawings manufacturing information on what the building was built, how it was built. And sometimes it requires a lot of research for us to be able to accurately do an energy model of the existing building. With the new construction, it's much easier because when architects and engineers are working on the design, they collaborate together. It's easier to find information from the manufacturers. However, when we go into energy modeling and energy audits, we do need to make a lot of assumptions. And in order to minimize these assumptions, we want to be able to collect as much data as possible. Currently, this data collection is a heavy, lengthy process when we need to send a number of technicians on site where they need to collect a lot of data. However, with the merge of the new tech, we can make this process much faster and easier for us. So, according to the ASHRAE levels of energy audits, if we take it at the highest level, we want to go and do an energy audit. One of the basic things that we need to look into is energy consumption. Those are energy bills from the buildings, trying to model and understand which month's building is using more energy, which month's building is using less energy. And then we're trying to correlate this building energy consumption with different factors in the building. That would be the habits. So what's the occupancy of the building? What's the functionality of the building? Is it a 24/7 building or is it 9 to 5 building? How is energy is being used during those occupancies and what kind of activities are happening during those occupational hours? Then we'll also look at the mechanical systems, how efficient they are, what type of mechanical systems are used, where we can optimize those mechanical systems. And then we're looking at our building shell, building envelope. That would be your windows, walls, roof, your enclosure. And that's where I would like to introduce, particularly in this context, the use of artificial intelligence and infrared thermography, where they both can contribute to your analysis of energy consumption via the building envelope itself, because we can collect extensive data about this particular part of the building infrastructure and analyze it better. And then all of these factors together, they come in and they contribute to our better ROIs, our returns of investment and capital planning. Because when we do understand how energy is used in a building and where is it mostly being wasted through, what are our low-hanging fruits, that will help us to tackle the issue in a more efficient way. So if we look into monitoring activities, when we're going through the actual audit itself and what's happening there, so we would be looking at the cost benefit analysis, right? What would be best thing for us to resolve to make the best return of our investment? Because most of the property managers and most of the stakeholders, from what they're seeing, is that they are not interested in a long-term endless paybacks that take over 50 years. And with current cost of energy and cost of the construction, it is sometimes hard to justify certain retrofits and certain improvements in the buildings because they don't see a right away return of investment. With those type of audits, when we can identify low-hanging fruits, we can actually make it more attractive for them and get a better budgets for retrofits for existing environment and expand on the budget itself. So we're looking at the cost benefit analysis, then we're looking at the equipment audit, because often equipment happen to be the easiest item to improve in the building. Because let's be honest, sometimes just changing a boiler and making more efficient mechanical systems would be more cost efficient than, for example, going and recladding entire facade of the building. So often equipment receives a first audit. Then if nothing has been found there, we go and see reliability and criticality audit, and that's where if there are any structural damage, structural integrities in question, so we make sure that everything is all right there. Then after that, we need to select an appropriate maintenance strategies, and that's where it would be very easy to monitor the building condition with the use of their infrared thermography, because it can give a very evident result of how the building is doing at different points of the time. And if you do a reoccurring infrared thermography, let's say every year or so, you can see a progression of a lifespan of the different building envelope elements. Then one of the things is with the infrared thermography, when you do collect this data, it does give you a lot of data points to look through, to sift through. And sometimes it can take hours and hours, go from data point to data point, to put them all together. Therefore, I believe that AI can really help simplify and make it more straightforward when we're processing this data. So you went and you collected, let's say, 500 images with the infrared thermography for a large facility. It would take about 1 to 2 hours for artificial intelligence, for the model to sift through this data, identify all the points, and then give you a feedback on the building conditions. From there, a professional can determine the maintenance actions and go through the review procedures. So when we're looking at the monitoring activities through the building, this is where AI and IR can really help us out. But just going back a little bit on the principles of the heat transfers, just to start familiarizing you with the infrared thermography and how the things work. When we're thinking about infrared thermography, we're looking at the heat being radiated from the surface. And in our particular climate, in the northern climate of Canada, it's very beneficial for us to introduce thermography to our energy audits, because in the winter times, we know that we will have heat escaping from the inside of the building to the outside, and we would easily be able to see those signatures on the surfaces of the buildings at the problematic areas of our buildings. So as we know, heat transfers from higher temperature to the lower temperature until it reaches the equilibrium. But then for the heat transfers themselves, we have heat transfers through the conduction, convection, and radiation. And thermography, even though its primary subject is to look into radiation, you can also detect the conductive heat transfers and convective heat transfers using those tools. So they're very beneficial for us. Just we need to know how to recognize different heat transfers and how to measure them. And just for you to let you know, thermal cameras, they capture the infrared rays, which are slightly different from the visible spectrum light. And it's important to keep in mind that things that we see on the thermal images themselves are not the things that we see on the visible light or RGB data that we're capturing. It's more about the heat from the surfaces of the that we're looking at that's being radiated, and then camera captures those wavelengths. Right now on the market, there are different producers of the equipment. Some of the equipment that I have worked with and been introduced to, the Floor is a relatively reliable tool that I really enjoy using and really helps me to identify some of the issues in the building envelope. But then this is where I want to start introducing you to use of the drones. Because when we're thinking about traditional thermography, when we take a camera and go outside of the building to capture the data, buildings in their nature are not easily accessible at all points that we want to see and want to be able to analyze and scan. Therefore, the industry now is coming up with the solution where you can do a thermal camera payload on a drone and fly a drone around the building. And instead of capturing 100 images, you can capture 10,000 images. So it's a much larger data set that you would be receiving, and you will be able to get to different nooks and crannies of your building to really understand if there are any particular areas that needs to be investigated additionally, or if there are actual issue occurring. From my experience, I find it very helpful to deploy the drones, because some of the particular areas like roofs or high fly above or going into the places where you can't reach. Very helpful. But another thing is that you are capturing a lot more data a lot faster, because average flight around the mid-sized building, I would say, would be maybe an hour, tops 2 hours, depending on the weather conditions. So it is a much faster data collection processing versus actually going on site, walking the site. And I find that collecting data with drones is a very good initial step when you're doing pre-assessment of the building. Deploying the drones, collecting this data, and quickly processing it with the AI really helps you to understand overall condition of the building. And outside of the building industry, infrared thermography together with the drones is actually used in a number of fields. Thermography itself is used or getting heavily used by different veterinary or medical imaging, then also conditions of the machinery equipment and research. And together with the drones, it's used in surveillance and wildlife monitoring. So this combination of infrared thermography and drones, I believe, initially was part of the surveillance development in the industry and for the warfare. And I believe at some point engineers decided that it would be not a bad idea to start using it for our building condition assessments. So overall process looks like we initially would go deploy the drone, collect all the data. This data would be processed with the AI in the computer software, and then you would receive some sort of reports, live videos, 3D models. That's right now something that's available in the industry, and a number of companies is doing it to help engineers and architects do initial assessments of their building envelopes. And overall, we can see this type of analysis being used in North America, particularly in the larger cities from what I've seen. So New York uses it quite a bit. Boston is picking up. There's some activity in Toronto, some activity in Vancouver. And I find that a lot of people who are interested in this type of work, they use a larger buildings, larger facilities because of the time reduction that it offers them. However, Europe also starts picking it up because Europe is becoming more rigid with their Europe is becoming more rigid with their restrictions on energy consumptions by the existing buildings, and any type of audit is becoming popularized there. And then Asia, being first of all one of the manufacturers of this technology, they're ahead in using it in different industries. However, I've also seen that they're starting to use it in the context of building energy analysis to identify how their buildings are, and they also favor this technology for their new builds, so warranty assessments. But how does this data collection happen? It's not only about putting a camera on a drone, sending it out there, and everything happens by itself on a magical whim. There is a number of steps that's required in those infrared thermography and drone technology audits. Before drones are deployed on sites in various times, what needs to be done is some sort of a site inspection, because drones have to fly a certain path, and to be able to set up an automated path, information about the site needs to be collected. Occupant surveys need to happen, because this information would be very important for the energy model calibration. Then flight planning happens, and then the authorizations need to be received. We are not allowed to fly drones heavier than, I believe, 0.5 kilo in Toronto. Don't hold me over that, but there is a certain weight after which we cannot fly. Thermography cameras are usually heavier than usual, and therefore those are larger, more industrial drones that are being flown. And for those, at least here in Canada, we need a permission from NAV Canada. If the site happens to be next to the airport or next to the military compound or any other high security areas, Then additional permissions, clearances will need to be received to be able to fly the drones in those areas. So it's not as straightforward. And then when the actual data collection happens, we would need to meet certain weather conditions, because thermography does not yield any meaningful results if, for example, it's rainy. Well, also drones cannot fly during heavy rain, heavy snow, and heavy wind. So certain humidity conditions will need to be present outside together with the wind to collect this data. Some of the people prefer to use thermography for moisture leaks detection. So they would wait for rainfall to occur, and then they would ask for the drones to be deployed afterwards to see if we can track the paths of water going through the building envelope. Thermography is really cool in that way. Then once the drone data is collected by itself, it might not be as useful until we start processing it and calibrating it. And calibration happens via additional sensors that are deployed on the buildings. And they conduct either the heat flux measurement through the envelope itself, or we are conducting blower door tests to understand the volume of air that's escaping through the due to exfiltration. So those are additional tests that need to happen together with the drone. Then all of this data, once it's collected, it takes 1-2 days to collect it if the weather conditions are right, needs to be processed via different softwares that a number of companies has and coming up with. And these particular softwares, some of them are pattern recognition. So you feed all your images through the AI model that recognizes all the patterns possible in your building envelope. Then you also use energy bills and additional data that has been collected for energy modeling calibration. So to understand and situate the heat flux that the thermal data is capturing, how is that related to the conditions in the building itself? And then after all of this, the delivery happens when it's either reports, videos, some sort of a portal is delivered to the client and whoever this client is. So during the data collection, some of the pre-operational things, I slightly touched on them before, but just to reiterate them here, during the site inspection, it's very important to do some of the basic roof walkthroughs just to understand where the drones can be taken off and going back in, because if it's a tall building, the drone itself cannot be deployed from the ground. It needs to be deployed from the roof of the building. So it needs to have some sort of maybe a meter square area where the drone can actually take off of the flat surface. Some of the preliminary facade identifications, and then also interview with the occupants and property managers to get a high level of understanding if there are any particular areas where the drones need to collect additional data from, or if we need to do additional flights around, I don't know, extra parts of the buildings and things like that. And the feedback from occupants and property manager is very useful. Most of those site inspections, they take maybe about half an hour or so. So it's a very time efficient step. Then occupant survey itself, I find that some of the companies prefer to send ahead of time questionnaires or data collection surveys type of thing for tenants in the building, whether it's residential, commercial, institutional, for them to say how they interact with the building and also answer some of the questions about the building usage. Then the flight path happens. So the zoning file usually that refers to when you're flying the drone, and if it's a large facility, you need to break it down, and then for this data to be collected in the same way that it would be processed, so the AI does understand where the data has been collected. So the machine needs to know which part of the buildings are, and usually most of the data that's collected via drone whether it's RGB data or it's infrared data, it has a geotag on it. So we can actually then feed this into a different software where it creates a model for you. And you know exactly where is it taken from. So zoning file is a way to organize those things. Where the sensors would be placed, and then weather conditions verifications, and then schedule. Because some of the buildings that, if we think about institutional buildings, right, high schools, there you cannot fly the drone when kids are in school in a session. So things need to be collected when kids are not in school. And for infrared thermography, it is an industry standard that it's the best to fly it at night, because a few hours after the sundown, to minimize solar load on the building envelope, because most of our buildings are concrete, brick heavy, and they have a very great heat capacitance. So some of this heat needs to be released back into atmosphere before we go and collect a whole bunch of infrared thermography. That way we can minimize the noises in the energy model itself. And then there are a number of authorizations that do need to be received when you're flying the drones, particularly here in Toronto. That's what applicable. We have the Transport Canada authorization that we need to receive. If we're flying over pedestrians, over the streets, drones need to be equipped with the parachutes. Otherwise, you need to shut down the street itself to fly the drone. And that means you need to call the police, get the police cars closing the streets, get special permissions from the city. And putting parachutes on the drones is a way to bypass this requirement where you don't need to close the streets. However, if the parachutes are not available, then yes, the street closure is required. And to be able to fly those heavier drones, a person needs to have advanced drone pilot licenses that are received just from Government of Canada. If you go on canada.com drone pilot, actually all the tests and exams are there. And usually exams are multiple parts, where it's a theoretical part where a person needs to respond to all the questions about how to fly the drone. And then they also need to pass a practice exam with the instructor to make sure that they are safe in their procedure flying the drones. It is advised when you're collecting a thermal data to have a thermography license. Those are usually received from Infrared Institute, and then working at heights sometimes required from actually property managers if you're going in tall buildings. And sometimes buildings have policies where you need to present them with working at heights training, just for the safety and insurance and liabilities. So this data collection for the drones itself, when for the energy model that would be built later on by the computer, some of the things that need to be collected, the inside temperature would need to be collected, outside temperature, surface temperature, then the weather data needs to be collected. All of those are usually collected with the sensors that are placed inside and outside of the building, so it's a very straightforward thing. You don't need to stand there with the thermographer to get this data. And from energy modeling standpoint, it is advisable to collect this data for multiple hours. And I'm not talking about 2 or 3 hours, I'm talking 24 to 48 hours, just to get the sense of the heat flux going through the building. Often from what I've seen in the industry, some of the sensors are placed in the buildings and left there for a number of days. The more data is collected, the better precision of the energy model results would be. Then we go through the visual data, and visual data itself is drone data capture. It's when the drone is flying during the day and captures a lot of RGB data. After that, for this data capture, when we're capturing the building during the day, it is advisable to do it when sun is in the zenith, so we have the least shadows, and overcast conditions are usually very helpful. Then we have the very good quality of the 3D models. operation performed around the noon, and that helps to reduce the shadow length. And when I say operation, I refer to the drone flight path. In the industry, pilots refer to it as an operation. Calm conditions and a consistent altitude, that's also required, because when the drone flies for the 3D model, it takes a much larger surface than the building itself. It doesn't fly just above the building. It takes a big overlap of, I would say, equal to the building size itself around the building, to make sure that it captures all the sides of the data. And then for the thermal data capture, drone flies that goes there at night. Also, sometimes the handheld data capture happens. It's usually 3 hours after sunset and up until 1 hour before the sunrise. And for this, all the atmospheric condition needs to be met as well. So when we do this data collection, we collected everything necessary for the building condition assessment. We talked to the occupants, we did the on-site measurements, and we did the thermal data collection. When this drone data collection happens, we are starting to putting it into computer and AI, and most of the times you are required to have a supercomputers available to you if you want to process it yourself. Those would be powerful either Windows stations or Linux stations. And I believe most of the architects that do 3D modeling, they do have the heavy-duty computers. So those would be useful when you're trying to process a large body of data. However, because this is a very new topic and emerging field, even with all the verifications that happened with the AI analysis and energy modeling, it is still advisable to have engineers, architects, and specialists review the outcomes of the energy models prior to deliverables and projects, because sometimes you can capture bugs in the code, sometimes you can capture mislabeling of the data, and then it just requires some additional calibration and revision. But we received this data, we collected this data. What do we do with this data? How do we analyze this data? And how do we interpret this data? When we're looking into energy loss through the building envelope, we can safely say that most of the losses of the energy, they happen through the elemental loss, and that happens via conduction, radiation, and a little bit of the convection on the outside of the building. Thermal bridges, so those are structural elements that we really like, that are very strong and keep our buildings big and tall. They often lose a lot more energy than the flat surfaces themselves. And then also infiltration and exfiltration losses that occur via different parts of the connections, when connections start wearing out, or maybe during the construction they were not sealed properly, or back in the day the certain technology did not exist, and we see that the building is losing energy via different connections in itself. So when we're thinking about those element losses, thermal bridges, and infiltration losses, they can be measured both quantitatively and quantitatively. So qualitatively, when you visually identify via pattern recognition that there is an issue on the image, and that's where thermography enables us to be able to see those things with our eyes. And then quantitative measurement, where we deployed all the sensors, and now we use those sensors to calibrate the thermal data and quantify energy loss through either different issues or through the elements themselves. So when we do all of those calculations, it's very important to consider climate, building type, materials, design, building usage, installation, and other external factors like regulations or efficiency goals. And this is where all the data that I have talked to you earlier, where we have been collecting, going on site, capturing it with the RGB drones, capturing with the infrared cameras, this is where they all come and play. And when we're looking at the different types of facilities, there is really no limitation at what type of the facility can be analyzed with this data. So pretty much anything works. And in all of those different facilities, and you can see on the screen, we can identify a various number of issues going from the thermal bridges. That's whereas through the structural elements, we see energy losses, and we can identify them qualitatively and quantitatively. We can identify the defective glazing and where actually the sealants are worn out and gas is being leaking through the window. So it's conducting and radiating a lot more heat than it's supposed to. We can identify the lacks of insulation with the thermography. I've personally seen cases where it was a residential building and builders pretty much forgot to insulate one of the units. So we're looking at the overall facade, and it was looking nice and even, except for one unit where they just missed the insulation for not known reasons. Very useful to identify the cracks in the facade, especially sometimes in the areas that are hard to reach and it's not evident to the naked eye where those could be. Thermography really highlights those parts. And thermography also can help identify moisture accumulation that's sitting behind the building facade, and maybe the surface is already on the exterior is dried up, but it just keeps sitting on the inside, whether it's because it has condensed down there or it's not being properly vented after the rainfall. A number of cases where we've seen the layer of bricks where you're supposed to have the whipping holes, and because they were for either drainage or for ventilation in the cavity purposes, they get clogged up with mortar. Often property managers think that those are mistakes and they need to be plugged in, and then water and dirt starts accumulating inside, and thermography really helps to highlight those issues, especially where it has been sitting there for a while. And traditionally, thermography has been around for maybe since 80s, 90s in the field, together with the energy modeling. Originally, it was required for the person to take the camera, go on site, capture the pictures, and then manually annotate them. There were no methods for quantifying energy losses prior. And now we're entering the place where we can actually, in a few hours, collect all of this data, process it with the machine learning, and then interpret the results. And maybe end to end, it would take you less than a week to do a large size building, versus earlier it would be only a few days of data collection on site. But how does AI work? Because I believe that AI is a very hot and trendy word this year. And I'm very glad to see that building science and building envelope specialists, they start to reaching out for that as well, and creating artificial intelligence and machine learning algorithms to assist them make a better analysis and make educated decisions about their buildings. So after this, all of the data collected, when we're building a large machine learning algorithm, we would need a body of data that already exists in the field. This data needs to be annotated. So before we had those AI machines where we just feed the data and it spits out that this building has 15 thermal bridges and 10 cracks, somebody had to sit and annotate thousands and thousands of images. Those were building science experts that have put time and effort into labeling every image hand by hand and creating this pool of annotated data. Then this pool of annotated data is handed off to computer science experts. Those are guys from the industry of the tech, and they start creating a training data model. So they start training this data, organizing this data, and doing the magic to it where there is a recognition of the patterns. And after that, they come up with this algorithm that also needs to go through experiment and tests where a number of experts, a body of engineers, building scientists, architects, they need to sit down and they give a test image to this machine learning algorithm. Machine learning algorithm labels it all, gives it back to them, and they need to say whether it's doing a correct work or it's doing not correct work. So it's test for validation. They're looking into the problems. And then if, for example, machine learning is not good enough, again, it takes a lot of data and work to make it up and running, there starts to be a feedback loop between computer science experts and experts that test the model for feedback until the model reaches necessary accuracy levels. And at this point, we have models that can, with 90% accuracy, label all the image data that is being fed to it and spit out an analysis of the building performance. And then after that, the model is deployed in the field and different companies use it. So this whole training process of the AI, there is a number of steps that needs to be happening. And this training process, when you train the data generation to the pre-processing and data training, it takes about, I would say, for the different issues that I showed you a little earlier, like a thermal breach, it takes about 10,000 data points. So 10,000 images that can contain a thermal breach issue that would need to be fed into this training process before it would be used. And this whole training data is used in the model, is used then for the issue detection in our energy modeling. And pretty much how it looks like when you give an image to the active model, it will go through the image and it will identify, over here we can see it's identifying all the types of thermal bridges or connection issues. That's just a little sample. And often when you're deploying an images to your machine learning, you can select the accuracy and how precise you would want to be. So it's called the confidence factor and the confidence factor or confidence percentage, where you plug in a number and you say that you want for the model to identify thermal bridges with 10% confidence. And then most likely the model will go and identify a whole bunch of things because it doesn't need to have a very high precision. Or if you go and you say that confidence factor would be 0.9, 90%, then it will go and select only items that it's more sure about. So you can actually play with the number of outputs that can be done, and those machine learning devices, tools that we have, they are actually very flexible and helpful in our work. Then the analysis can be put together into the reports, and Infrared Thermography Center, they do standard reports. In the industry, I've seen the reports where they actually talk about, for example, things like energy losses through the different elements. They can break it down, so how much moisture area it has been detecting, and how do your findings compare to different baselines that, again, various people prefer their own way to compare the results, but people are becoming rather creative in how they want to have the deliverables. And now we're actually seeing an emergence of live detection, where it's actually a camera is deployed on site and it's giving a feedback loop to the it's giving a feedback directly to the system. So it's being a video capture, and then video is being annotated with the different issues live. So it's also coming out there in the field. And then different 3D models. So for the RGB data that I was mentioning earlier, that's collected via the drones. What we do is that we can actually process it with a number of softwares like NeuralPix for the DJI. There's a number of programs available on the market where you feed your 3D data into those softwares and they create a photogrammetry 3D model. And I believe you can actually do area measurements with those 3D models, and the accuracy is down to 1 centimeter, which is pretty incredible what we can do. So Combining all of those things together, AI, together with the 3D models, together with all the sensors, we're able to receive a very good understanding of where our building stands in a very short period of time. Because as I mentioned, if we combine all the tools together in one process, it would be plus minus 1 week. Again, some people use it separately. So one company would be doing thermography, another company would be doing 3D modeling, another company would be doing actually data processing. Really depends who you're talking to in the field, but if we put them all together, it can be as short as a few days for smaller buildings and about a week for a medium-sized building to do. From the point of close the project, we need to collect the data, deploying the drones, to receiving your results about your building. And in the industry, it's known that energy models, there is no perfection in them. It's a never-ending cycle, and everyone has to decide for themselves at which point they say it's good enough and let's move on. And I would say with this type of analysis and energy audits, precision might be not as high as a traditional energy analysis. When we measure everything, we spend a week on site and then we spend another 4 months doing energy plus model. However, this model is still accurate enough. It sits in about maybe 85% accuracy, and it allows people to do fast decisions about their budget distribution, about how the buildings need to be retrofitted and maintained, and what would be your low-hanging fruits. So depending on the use case of the energy model, this type of work comes very useful for people who are doing budget distributions, for the people who are doing initial assessments, and for people who want to see what type of work would be beneficial for the building. So then some of the applications of these energy audits, some people use it for the cost savings. So identify which element is the worst in your building and just fix that instead of doing a full-on retrofit. Energy efficiency, it helps them to understand where your building stands at and what kind of work needs to be done. Compliance with regulations. From what I've seen in New York, they passed a bill where it is required for each building to report the energy consumption. And often the high-level energy modeling would be used for them to assess the energy consumption in the building and what part of the bills is going to different parts of the building envelope. Well-maintained buildings do have an increased value. There is definitely environmental impact in reducing our energy consumption. Also, a better buildings, they make a better comfort for the tenants, as well as when we do energy audits on a recurring basis, we can predict the maintenance and we can foresee issues coming from a mile away instead of being hit with them in the most inconvenient moment. And also there are incentive rebates. We've seen some of the programs from government where they propose if you do a retrofit, you do an audit before and after, they will give you money back for this retrofit. And that's where energy audits actually useful and applicable. And then there is a number of applications of them through the certifications and programs. LEED recognizes thermography as a part of their requirements. BOMA, Brilliant Well, and Passive House, they all have a place for infrared thermography done via handheld cameras or via drones, depending on the accreditation itself. But they all suggest doing it as a part of the requirements to receive their accreditation. And then there's also some of the federal programs that we can see that require energy audits as well. And if a person or company or facility manager wants to be a part of one of those programs, whether it's on the federal, provincial, or municipal level, they would need to have an energy audit done in order to receive their rebates. And then for the property owners itself, we found that well-maintained buildings usually have a higher rent and they go for higher value. Sometimes we've seen that future property owners request to have an energy audit done. So before they know what they're signing up for, they want to understand where the building stands in. And also we've seen that for a number of the insurances that people like to do energy audits for after the construction, for the commissioning the properties, and for knowing that the items that they are insuring is going to last for a while. We've seen the case where a new building was built and it was targeting to have a net zero status. However, builders itself did make a number of mistakes, and thermography helped to reveal and hold these builders accountable before the building was decommissioned to its users. And the main, again, users of these energy audits would be older buildings, larger facilities, whether healthcare or institutional, and number of different businesses. They also want to be able to do energy audits. And last part that I wanted to quickly walk you through are some of the case studies that I participated in and that are out there. So one of them would be a healthcare facility. Another one would be a large institutional project that was done here in Ontario, and the last one would be a commercial building. So first one is a healthcare facility. It's a landmark building in the downtown Toronto. And for this building, more than 5,000, about 5,000 data points have been collected. Throughout the building envelope, over 250 issues have been identified. However, the entire data collection has taken about a day, and duration of AI analysis was about 50 seconds per image. So it was feeding all the data. It took an extensive period of time, but it was very quickly that we got a turnaround on these data points. And we were able to identify that walls were the biggest offender in the building envelope. Next after them were windows, and there was big opportunities for the GHG reductions in the buildings if certain items have been met. Another issue with this, caveat with this building was that this is a healthcare facility. They can't just shut it down and do renovation. They had to do a partial renovation. And with this type of audit, we were able to help them identify which parts of the building need to be addressed first, which parts next. So the hospital itself could continue working seamlessly and just help going through this with the least effect to the property and doctors and patients and everybody else. And some of the issues that have been identified there was a large number of the thermal bridges, there were some inconsistent installations, and this analysis really helped to sort and organize all of those issues and see where they are, and that, for example, moisture and cracks in the assemblies, they needed to be addressed first before all the energy-related elements. The second case study that I would like to introduce you to is the large-scale institutional project. And this institutional project is contained a number of buildings, 5 buildings. So about 25,000 data points have been collected. And at this time, the AI has really advanced forward. So I think it was about 5 minutes per building that this was taking analysis. So altogether, it was about under half an hour of a very heavy supercomputer work. Across 5 buildings, over 1,300 different issues have been identified, and we were able to receive this information about 1,300 issues from after just 22 hours of data collection. So 5 buildings, less than a day to collect all the information around it. And this facility was, because it was a campus that has been scanned, what property managers received there is understanding which buildings are best performing, which buildings are least performing, and where they need to distribute their funding for maintenance and operations. So one of the things is that they were planning to do retrofits on the roofs, and we're able to identify that actually roofs are performing pretty well. even though they were older roofs, but they just managed to keep them so well. However, the windows were a bigger contributor to the energy losses in this campus, and we helped them build out a window replacement program for some of the buildings where they actually needed help to get the best return of their investment. Last building that I would like to introduce you is a Canadian International Airport. And airport itself was a very challenging from the standpoint of the execution. To fly drones at the place where you have planes is not as easy. We had to receive a lot of permissions. There were extensive conversations with the NAV Canada, and we had opportunity to fly the drone only when all the planes have been grounded. Was it challenging? Yes, it was very challenging. We had to collect the entire airport data in 12 hours because that's as much window we have received. However, if a person would had to go and collect this data manually by hand, I believe it would be a very difficult process, even worse than what we had to go through, because it would be very time consuming and we cannot ground planes for that long. So it probably would need to be partial and inconsistent. So some of the issues have been identified. And again, here the data processing was a little slower, 50 seconds per image. That was at the time when the technology was just emerging. And that helped to just look at the large facility and identify different issues that were present in the building envelope and give property owners and managers a really good understanding where airport stands at from the energy point standpoint. And then where they need to focus their attention and budget on remediating some of the things. So roof was particularly interesting in this building, and we helped them to identify and prioritize issues on the roof to make renovation more seamless. So just to quickly wrap up with the conclusions, building energy audits, they can really help us understand where our existing buildings stand at, and they can help us increase the efficiency, do effective maintenance, increase the property value, comfort, and also address the equity of our buildings. When we start introducing IR and drones and artificial intelligence, we can really collect a lot of data. We are able to visualize this data much easier. We're able to prioritize and make our retrofits more cost efficient, and we can get a much better precision from our analysis. And with the AI, we can really enhance the accuracy. We make the process a lot faster, and predictive maintenance becomes a lot easier. It's not as heavy, it's not as time consuming, and then it helps for us to be consistent with our buildings, with our analysis, and with our results. So, and with this, I would like to wrap up my presentation and open floor for discussion and for any questions you might be having.
Thank you so much. Just a reminder for those of you who would like to submit a question, please, this is the time now to have questions submitted into the Q&A button. And I don't know if Ashley, you've got some questions already, or Raisa. I think we have a couple of questions.
I have a question, yeah.
Okay, please.
Thanks so much for your presentation. Appreciate it. When you were talking about older buildings and these energy audits, how many audits would you recommend per year? Because it sounds like with an older building, could be some more problems. You know, they're not as modern as everything else. So just curious how many times a year you'd recommend an energy audit for an older building?
For an older building, I think it depends the climate that you're living in, because some of the climates can be a lot harsher and they are more destructive for the buildings than the others due to either freeze and thaw cycles or due to exposure to the solar. So those, I would say, would be advisable every 2 to 3 years. However, if you're living in a more moderate and mild climate, I would suggest maybe 5 to 6 years.
So just a follow-up question. So for the case study you showed earlier for the older building you worked on, how many times was there an energy audit on that particular building?
So for, let me just pull up. I'm not sure if that was the one that we're talking about, but let's assume so.
Yeah.
I would say that for this one, we were the first one to, well, I was the first one to actually go in and do this type of analysis, but the property managers themselves, I believe they've been rather proactive and they were doing it every few years.
Okay.
But for the thermography with the drone and full compliance of everything, well, it was done first time about 2 years ago, and I believe that they want to do some renovation work and then do another analysis afterwards.
Okay. Okay. Excellent. Thank you so much.
Great. We've got a few really good questions coming in. So the first attendee, Ned, wanted to ask if you could explain how to track water leakage in a roof specifically, or specifically a sloping roof.
So for this, what happens for the moisture, from what I've seen in the field, when the rainfall occurs, it's advisable to wait for about 24 to 48 hours, sometimes a little longer, sometimes a little shorter, depending on the atmospheric conditions, to see if the water goes through the normal path where it's being drained from the building. If you go straight after a rainfall, you would get a lot of misreadings and noise in your readings. The data would be not as reliable. But then if you go after a few days, usually thermal cameras are capable to depict where moisture is still sitting on the surface or behind the surface. Particularly here in this airport, we were able to capture where it was, I think, about 4 days after the rainfall. And from the naked eye, the surface maybe looked slightly different, but not as much. But then inside, it was captured that the moisture was still sitting in, because what was happening is that moisture has a different thermal capacitance versus other elements in the roof, depending what it is. Usually it's insulation. And because the moisture was sitting inside of this insulation, it was giving a different reading to the system versus the good uninterrupted areas.
Okay, thank you. And Milan wanted to know how you use sensor data in your analysis. How are they correlated with IR images? And how many sensors do you use, and where are they all located?
So let's open this up. First was how the sensor data is related to the IR, right? Usually when we go on site, what I would do is that I would do a handheld camera with at the areas where we do deploy sensors. So you deploy sensors usually on the building envelope itself to capture heat flux through the wall assembly, window assembly, door, depending. And then I would do a few IR images of that particular data. So from the sensor reading, I would know what's the heat flux for this particular area, and then I would be able to extrapolate it to my thermography data. So it's sort of equating it together, and then from there, the system does a further extrapolation where a number of those sensors is deployed, right? It's not only one sensor. And we're able to correlate the thermal reading, and because at every thermal reading, when you capture the IR data, it's not just an RGB pixel. Every pixel has a temperature recording. So it actually records the surface temperature of the entire image, and then the system reads all of those pixels. We're able to calibrate accurately the temperature on those pixels via the sensors that were deployed, and that way we can further on extrapolate into energy losses through those different issues that are identified in the IR, because we're able to get a very accurate surface temperature reading from our IR data. For the number of sensors, it depends on the building itself. The larger the building, the more sensors obviously you would want to deploy just for the accuracy and consistency of the findings. I would say that it is a bare minimum requirement to have about 5 to 10 sensors per element. So it would be 5 to 10 sensors per windows, doors, roofs, and walls. And then the larger the building is, or if the building has many different construction. So what I mean is that some of the wall assembly would have metal on the exterior, right? And then maybe they were insulated, but then, or maybe it was an addition done to the older building, and older building was masonry, and then the new building was hollow frame building. It's very important to deploy sensors on all the different various types of the assemblies, of the exterior assemblies, to accurately capture it.
Next question, there's a few more coming in, which is great. Snowbird wanting to know, are you able to give a ballpark number for what it would cost to prepare an energy audit and propose strategies for a mid-sized institutional building?
How about this? I will leave my email.
Yes.
And if people want to reach out, because I'm not sure if I'm allowed to do this in the format of this webinar.
So I know, and there's so many, I would also give a similar like lawyer answer, like it would depend on so many factors, right? I'm sure what the cost is. So that's a great, reach out to our speaker for that information. Okay, so the next question is, would you say that most analysis are requested by the property managers?
Yes, I would say that most of the analysis, from what I've seen, is property managers are a big part of it, but also portfolio managers. So for example, there's a company that manages 50 bank branches, and they need to spend XYZ dollars on maintenance of these bank branches. They would reach out for this type of analysis because it's a quick turnaround to be able to identify which branches are in the worst conditions and would need more money spent, instead of equally distributing this XYZ money across all the bank branches. That's one type of the client. Another type of the client where property managers themselves reach out to us. But then I've also seen a lot of other firms like large engineering and large architectural firms reaching out for this type of analysis to be an additional package in their work and whatever analysis they do.
And I guess the motivation is then mostly like a financial cost savings.
Yes.
Yeah, okay. So William is asking, I'm often requested to do a comprehensive building assessment, including an interior assessment and exterior finish and durability review. Could the drone images help with comprehensive building exterior? How would your study complement the total building review, and how would I present this to a client?
I'm so sorry. I think I cut you out a little bit. Could you please repeat that?
Yeah, so it's a longer question. So basically he's saying he is himself as an architect, I'm assuming, often asked to do a comprehensive building assessment, including an interior assessment and an exterior finish durability review. So what he wants to know is, could the drone images, I think that you're presenting, help with that comprehensive building exterior assessment? And how would your study complement the total building review? And then how would he present this to the client? Or how would it get presented to the client?
Gotcha. So one of the things that I haven't mentioned here, to start with the interior, drones, obviously we cannot go inside with the drones, and drones are not X-rays, unfortunately. It would have been so cool if they were. And what happens is that we have devices and tools to map out interior 3D as well. Sometimes clients request that, to have not only 3D of the exterior, but interior. And there are different tools like Leica, where we can go and actually do the capture of the interior 3D. And then with the handheld cameras, we also can capture interior conditions of the building as well. But it's just more manual areas. However, My personal approach to that was first fly the drones, identify the issues on the exterior, and then go and see those areas from the inside of the building. Because usually what happens where we have a better areas on the exterior, there are lesser chances of issues occurring on the inside. Still present, still possible. It just my first start point would be to investigate those areas, and depending on the accuracy that client wants to receive and how precise we want to be, how much time to spend there. So that would be one approach. And then overall, this condition condition assessment can really help get an overall understanding of the building, and where, if you do want to do a more precise assessment, where do you need to narrow down. So it serves sort of as an initial ground step. It's very quick. You send the drone, quickly collect the data, get the feedback, and then from there, what you do is you narrow it down to additional, because I've been in the cases where the work was done in States on some warehouse facilities. We did deploy the drones to fly on the exterior, collect all of this data, and then we identified certain issues that were really resonating with the client. They were very surprised, and then for validation, we went in and actually flown down to States and found verifications of our findings. But our findings were a very good step to open this conversation and identify those alarm bells in the building.
Oh, thank you. And then the last question that we've got right now is just a question if you could explain the annotated process for the images by envelope consultants.
Yes, so when the machine learning algorithms were designed initially, what needed to be done is that all of those issues that machine learning is able to give us now, originally there was a group of scientists, building scientists, that had to sit down, who has been doing thermography for a while, refer to some of the Infrared Institute recommendations, because this has not been invented now. This has been around for about 30 years or so. And the Infrared Institute, they have started this branch of building science, and they have actually separate training for the people who want to do building envelope assessment with the infrared thermography. And the group of building scientists, they sat down and they went through all the images collected by drones or handheld cameras from a large number of buildings, and they were manually identifying those areas in a special software. There's software available there in the industry, in the market, in the computer science world. I'm not as tightly familiar with them, where you can actually have any type of visual data that you're giving to the computer, and then there with different shapes you identify those issues. Then you have a pool of 5,000, 10,000 images for just this particular issue. So it's, I think, 15 to 20 building scientists had to sit down and spend at least a year of work, morning to evening, of labeling this data to be able to build these machine learning algorithms, where the software, when it sees the image, where it looks at this image, it looks at the thermal patterns, and thermal patterns, they are part of it is visual, right? That where it sees that comparison of the colors. So it was very important to use the same color representation of the infrared wavelength. I think this one is called iron red that they were using. And then it also looks at the temperature of the pixels. So if we have bright yellow next to the purple, and then we have a temperature that's dropping, I would say between from, let's say, -3 to +5, or certain parameters, so those parameters were also plugged in, then machine would say that most likely this is a thermal breach, or most likely this is this issue. So there are a number of factors that you need to repetitively tell algorithm before it's able to identify it in all other test data that you're giving it. And when this whole process was happening, I would say that from 5,000 images that are required to train a model, maybe 4,500 images was used as a training material itself, so labeling occurring on them, and then 500 images for a test subject. So you randomly give those 500 images to the algorithm, and it has to produce a feedback loop for you. I hope that answers the question.
Oh, great. Well, I'm not seeing any follow-up questions, and I'm seeing everybody is still on the call, so I get the sense that everybody's been very attentive, and the information that you presented has been incredibly thorough and helpful. So we're going to close. I don't know if you had any parting thoughts, Raisa, before we just sign off with a few closing announcements. Yeah, did you want to add anything to the presentation, or just to remind everybody to contact you if they have any other? Yeah.
Sure.
Okay, great.
I'm not sure how to circulate my email, if we can send it after to the participants if they want to reach out for the additional questions.
It can be sent in the survey. Is that okay with you?
Sure. Yes.
Okay. I will make sure your email is included so that if our attendees have any questions, they can contact you directly. I'll include it in the survey.
Of course. And I would like to thank everyone for the questions. I really appreciate them. And thank you everyone for coming. It's a pleasure to be here.
Great. Yeah, well, thank you so much. And it was a great discussion, like Raisa said. So just a couple of announcements before we sign off for the day. Next week, we have a webinar for this Thursday, August 28th, with the title Lake City Way Studios in Burnaby. As I said at the beginning of the session, we will be reporting those hours for those of you who attended 80% of the on-ed session today. And just allow us some patience while we upload those hours. And we will also be sending you, I believe, a slide, or if we can get them scaled down a little bit, and a link to provide the OAA with feedback on today's presentation. They always appreciate everyone's feedback. So please do take a moment to fill that out. Thank you so much for everybody's attendance, and have a wonderful remainder of the day. Bye-bye, everybody.